Okay, so as last week, feel free to, you can have this on in the background and just listen along. I'm not expecting participation. By all means, ask questions. Just unmute yourself and shout if you have one. I am going to take the Schrodinger equation, try to explain how to use it for a simple situation. This session may well end up being a bit of a maths lesson. However, it will give you some idea of how you can go from a mathematical equation, which is based on, let's face it, a few postulates and an educated guess, I guess, on Schrodinger's part, and with it end up justifying and producing, as we'll see, an energy spectrum. It's almost as if the idea of energy levels just pops out if you grind the mathematical handle. So I'm going to start by writing the Schrodinger equation down and just highlighting some features of it. The full unadulterated version involves both position and time. So this is, I'm just going to write it out. And then, so that's one form of it. In fact, let me just write the full version out. And this is one dimensional. I can't be bothered writing it. We could write a vector equation, but this is for one dimension. And phi is a function of x, right? Remember, wave function is this wave, well, it's a function which tells you the state of a system. So that's the Schrodinger equation for one dimension. And you'll notice that it depends on, it has, I should really add, for the wave function, it also has a time dependence normally, because obviously systems can change their state as time progresses, right? So we've got wave function is a function of displacement or distance, position, I should say, and time. And we've got this term, which tells you something about how the state of a system will vary as time goes on, because it's got a dt in it. And then we've got this part, which tells us something about the positional dependence of the wave function. This can be rewritten, actually, this bit on the right-hand side. You can take out the wave function as a common factor and end up with something like this. And this thing, if you've done any reading ahead, this is called a Hamiltonian. And it's often referred to as an operator. And the reason it's called an operator is that it's operating on the wave function. So that's called a Hamiltonian. Sometimes you'll see this equation written like this. You'll see the equation written h times the wave function equals energy times the wave function. And this h thing is just what's in that bracket. And then this is the energy of a particular state. The reason I highlight this version of it is that those of you who do maths might have come across something called an eigenvectors and eigenvalues. It turns out, again, just ignore this if you've not come across them. This is called an eigenvalue equation because what this is doing is we've got a wave function here, which is kind of like, has many similarities of a vector. We're operating on it with a operator. In maths, you might consider like multiplication by matrix. And then you generate and a value, a scalar multiplied by the function. So in maths, when you take a matrix and then multiply it by a vector, you get an eigenvalue and the vector back again. So this has got similar structure to matrix multiplication. That's just an aside. If you've read about quantum physics, you'll have come across a way of treating quantum mechanics using the maths of matrices. So that's just a sort of hint at where that comes from. These two terms, I'm going to de-highlight these. These two terms, this term and the orange term, Vx, are two things that you're already familiar with. They are, I should have given myself more space, kinetic energy, no, although I admit minus h bar squared over 2m d by d2 by dx squared is not immediately recognizable as the kinetic energy, but trust me, it is. You've got a 2 and an m in there at least. And then this Vx is potential. Potential or potential energy. So the Schrodinger equation, in terms of its structure, is saying something remarkably simple. It's suggesting that how the wave function varies with position and time has a lot to do with the kinetic and potential energy of the system, which is why we bang on about them so much in physics, okay? As you do more and more physics and talk about fields in due course, first years, you will talk about kinetic and particularly potential increasingly frequently, okay? There's a reason behind that. It's that potential and kinetic energies are fundamental to how the universe, how quantum mechanics, how quantum field theory operate. Now, we don't want all of this. I'm not going to solve this whole thing and look at every last detail. I'm going to simplify it. I'm going to use this situation called the particle in a box to show you how you work this one out. Now, a particle in a box just means you imagine an infinitely deep well. Right, this is an analogy. An infinitely deep well, and you've got a particle sitting at the bottom of that well. Now, if it's infinitely high, it's going to require, that particle down here is never going to escape. There's zero chance of it ever getting out of the well. So what this infinite potential square well means really is that the particle is lying in a potential well. It could be gravitational, it could be electric, and it's completely trapped between x equals 0, let's say, and x equals L. So what we're doing is we're confining a particle to a line in one dimension between 0 and L. Now, you might think, and so the sides of this potential well are infinite. There's no chance of the particle getting out. You might think, does such a situation actually exist? Is this just a sort of imaginary simplified scenario to help people understand how to solve the equation? It is used as that, but it's possible in condensed matter systems. So in solid, if you study solid objects, often it's possible to contrive or approximate certain environments for, say, electrons as this particle in a box, a trapped electron. So it acts as an approximation for certain real physical situations. So it's not just a complete fiction to help students understand quantum mechanics. Now, we've got to define, you see this first step here, define the potential energy. That's the first thing I'm going to do. And we're going to say that the potential V of x inside the box, so for x is greater than 0, but less than L, or equal to L, is going to be equal to 0. And the potential energy outside of those walls, if you like, so for x is negative, less than 0, and x is greater than L, is infinite. So basically, this area is, the particle cannot get into it. So this is the mathematical way of saying we've got a potential well with infinitely high sides. The particle would need an infinite amount of energy to escape the potential well. So it's well and truly trapped. Now, I'm going to write the Schrodinger equation down. This is where it starts to get mathematical. Those of you who do further maths and are in the second year are going to be able to stomach this better than the first year. I will try to outline what maths I'm using when. I'm going to write the equation down. So again, now we don't need to worry about this bit because all I'm going to do is think about what's happening at a particular time. I'm not going to think what's the time dependence going to be. I'm just thinking, how does the wave function depend on x? You can use the version of the Schrodinger equation then, which looks like this. And I'm not using curly D's anymore because we're definitely one-dimensional and we're not worried about time as a second variable. So this is the equation actually that we want to solve. And that equals energy times the wave function. Now, V equals inside the box, Vx, I've already defined it to be 0. Therefore, the equation simplifies to this. Because this is 0, that disappears. There's the equation. Now, this is called, if you're interested, a second order because of the second derivative, differential because it has...
First of all, a disclaimer.
Oh, hang on a minute.
Unlike A-level material, which I've taught rather a lot before.
Give me 1 minute, that's the video.
What I've never done, really, is teach this properly. So it's...
Sorry, I just had the video from last week processing, so I can't put it up somewhere. That was strange. Second order differential equation. The reason it's called a differential equation is it involves a derivative, like this bit. Oh. So if you already know, those of you who've done Newton's second law, i.e. all of you, have already come across a differential equation because Newton's second law can be written m d2x by dt squared ma equals f. So you've already come across these kind of equations without knowing it. Now, if you do further maths, you'll learn how to solve these. Today, I'm just going to do it for you. It's easiest to rearrange it into this form over h bar squared times the wave function. And then you can, in fact, let me rearrange it so that it equals 0. So I've rearranged and then brought both terms onto the left-hand side. Now, I'm not going to teach you further maths right now. To solve this, and I'm happy to show people this later who want to stay, to solve this equation analytically, meaning using mathematical methods to get a proper solution, requires you to know something about complex numbers and how to solve second order differential equations. And it's for those of you who have some background in that, I can do it, but I'm not going to do it to start with. What we can do though is guess a solution. And I'm going to simplify this by making the substitution k squared is 2me over h bar squared, because then I can take this horrendous looking group of letters and make it do this, plus k squared wave function. Okay, it's just to make things look, it means that I have to use less ink later on. Those of you who have done SHM will recognize an equation of this form. And when I say to you that I'm going to guess the following solution, that will not be surprising. So it turns out that a differential equation like this has solutions which are trigonometric functions. They're oscillating like this. So already we're going to find that our wave functions for an electron or particle in a box are going to have some kind of oscillating nature to them. A bit like, okay, so remember what I said about standing waves last week? Well, okay, you'll see. So that's called the general solution. And does anyone know how you could prove that that function is a solution to the equation above? What's the easiest way to show that it's a solution?
Square it.
Square it. Squaring it wouldn't, we've not got a wave function squared in there. What we can do is just substitute this into the equation. So I can prove it to you, because if you differentiate, well, in fact, you can go away and do that as a task. If you substitute my guessed wave function into the equation, it will work out. So if you put it into there, it will equal 0. And hence it satisfies the equation. So it's a solution. So to go from the general solution to a particular solution, we need to have what are called boundary conditions, which are as follows. Because the wave function has to be continuous, you can't just have, you know, it being discontinuous, like going from one value to another. And because the particle can't be outside the box, so these regions here are disallowed. You can't, the particle can't be out here. So that means the wave function at here and here has to take the value 0. It has to be. So the wave function at 0, x equals 0, and the wave function at x equals L both have to be 0, because whatever the wave function is in here, you have to have a 0 value at the edges. That limits us to what kind of oscillating functions we can have. Okay, if we want both ends of the wave function to be 0 here and here. So how do we apply those boundary conditions? If we want lambda of 0 to equal 0, so this means, let me write this more clearly. Lambda at x equals 0 equals 0. What that means is, if our general solution is this, lambda 0 is going to be a times sine k times 0, if we put the value of 0 in for x, plus b cos k of 0, k times 0. Now, sine of 0 is, well, 0, so that disappears. We want this whole thing, remember, the wave function at x equals 0 to be 0. And that means, because cos of 0 is 1, that tells me that b has to be 1. Which means I can now modify my general solution, because I know sorry, I'm being stupid. That means b has to be 0, because if cos of k0 is 1, and we want the product of this to be 0, then that has to be 0. So that means the general solution isn't just a sine kx plus b cos kx, it's just a sine kx, because we don't want b, we've just worked out that b has to be 0 for this situation. It also makes sense because, of course, sine starts at the origin and does this, whereas cos would start up here and come down, and we can't have the wave function having a value at x equals 0. Now, what's the next boundary condition? So that was the first one. The second one was that we want the wave function to also equal 0 at the other end of the box, as it were. So that also equals 0. So let's see what we've got. At the moment, we've got this function, this general solution, or general solution. If we put x equals L into that, we get a sine k times L equals 0. Now, this next bit is something that you won't have done before necessarily, but someone can answer this question probably. When does sine, if you've got a sine function, when does that equal 0? What has to be in this bracket for sine of it to be 0?
$180 or pi or whatever. Yeah.
180 degrees.
Yeah.
Or pi radian, or any multiple of that, correct?
Yeah.
So what about this? What if KL, what's inside the bracket, is an integer multiple of pi? That will mean that whenever, if this is true, KL equals n pi, that means my equation a sine KL will always equal 0, provided that this is true. So actually we can say, well, that means k is going to be n pi over L. So in fact, my solution is further modified and honed so that we have this. N pi over L times by x. So I've just replaced the k in here by n pi over L. So that second boundary condition gives me some information about what's inside the sine function. Right. You know what? We can draw some of these. If you draw, if this is position, if for n equals 1, you actually get that. For n equals 2, if you went into Excel or whatever and plotted it, you get that. For n equals 3, you get this. So what we've already done by using this equation that Schrodinger made an educated guess to find is, for a particle in a box, the wave functions are of this form. Okay, now I wouldn't be surprised if you didn't follow all of that, but all I've used really is, you know, second order differential equation solution and some trigonometric functions. Does anyone remember what the wave function squared tells us? What's the significance of squaring the wave function?
They're all positive values.
Say that. Oh, sorry. Say that again. Who was that? Jessica.
They're all positive.
Oh, Mirabel. Yeah, certainly. The value, whenever you square a wave function, you end up with a positive number. What's the physical interpretation of the square?
Probability. It's the
Good. It's the probability of a particle being in a certain region. So if I square the wave function, it tells me probability. A squared sine squared n pi x over L. But if I add up the probability across the whole box, if I sum up all the probabilities of for all the x's over the whole box, which amounts mathematically to doing an integral between 0 and L, what does that have to equal? If the particle is going to be found in the box, definitely. If this is probability. So this is the probability of being in the box. What does that have to equal?
1.
That has to be 1. Because I've already said there's no chance of the particle escaping. This is, again, we can work out now what A is. Has to be, in order to have something called a normalized wave function. So if you've ever heard the term normalization, that means choosing the constant in front of our wave function such that the integral across all of space is 1. Because that's not necessarily contained in the Schrodinger equation, we need to specify that. So normalization, find constants such that the probability of finding the particle anywhere is 1. That's kind of physical, like common sense, intuition makes that like a must. Probability of finding particle anywhere is 1. Right, that's a, we need that, right? So, how can we find A? Well, even over the first years, have you done the integration of trigonometric functions?
I don't think so.
Right. So, this is the problem. We want this to be true and we want to find A. Now, if this were a normal lesson and it weren't Friday afternoon, and this weren't an extra session, I would maybe get you to try this. And you're more than welcome to try it without looking. But basically, in order to integrate sine squared, you want to get rid of the sine squared and write it in another form. And the way you do that is by using something you have come across, which is a double angle formula, which is this. And so you can rewrite sine squared x as 1/2 times 1 minus cos 2x. And that is something that can be integrated easily. So the a squared over 2 comes out the front because they're constants. Then you get 1 minus cos 2x. Oh, in fact, it's not just x, is it? It's 2n pi x over L, because this is inside the sine squared, dx equals 1. Now, I know some of the second years are desperate to do this themselves, so I'm going to leave it to them to show that, not right now, but in their own time, to prove to themselves that A has to be root 2 over L in that case. For that to be the normalization condition up here to be satisfied, A has to be root 2 over L, which means the final wave function, set of wave functions for a particle in a box are root 2 over L sine n pi x over L. Notice I've used the subscript n here because obviously we can have integers 1, 2, 3, 4, 5, 6, 7. So you could, I suppose, write for n equals 1, 2, 3, etc. Now, this is the final bit you'll be glad to know. Remember earlier on, we wrote that k squared is 2me over h bar squared. So this bit. Like earlier on, we said that k squared was 2me over h bar squared. And up here, we found that we needed k times L to equal n pi, so k is n pi over L. If we combine those, what do we get? We get the following. N pi over L squared equals 2me divided by h bar squared, which rearranges to E equals n squared pi squared h bar squared over 2ml squared. And I'm going to put a subscript next to the E because, again, we've got n appearing here. For every different wave function, there is a specific value of E. Oh my God, don't do that. There is a specific value of E for every wave function. H bar, by the way, I should have said this at the beginning, H bar is just H over 2 pi. It's just a form of Planck's constant. Now, these two equations, we've basically done what we set out to do because I've basically showed you that there are n wave functions, each with a specific value of energy, right? Now, these functions and the energies, where have they come from? They've come from this equation. So for each of these, so for a particle in a box, you have a ladder of possible states, n equals 1, n equals 2, n equals 3, which look like this. And each of them has an energy. That has an energy, you know, pi squared h bar squared over 2ml squared, n equals 1. This one has an energy of 4 pi squared h bar squared over 2ml squared. This one has an energy of E3 equals 9 pi squared h bar squared over 2ml squared. So I've produced for you a spectrum. It's inescapable. If you solve the Schrodinger equation for a particle confined in a box, you generate a series of distinct wave possible wave functions or states, and corresponding energies. The electron or quantum particle has to be in one of those. It can't exist with an energy in between two states. It can only have one of the ENs, which is given by this box. So we've got exactly what I promised. I've shown you why and how you get an energy spectrum. The why of it is less clear, but that's how it drops out of our equation, which is based on some of the assumptions and postulates that were made last session. And hopefully you can see the similarity between the standing waves on a string, fundamental first harmonic, second harmonic, and the maths of what's going on here. So that, in my mind, is quite satisfying. And possibly you can understand, therefore, why standing waves are on an A-level syllabus, and possibly understand why SHM is on an A-level syllabus. There are lots of reasons, but one is the maths that goes into solving this equation here is the same as that which goes into solving a simple harmonic oscillator. You always come across these similarities in different areas of physics, okay? There's sort of cross-pollination and links between the two, and mathematical isomorphism or similarity between different areas. So what I've just done is what you'd cover in a second. I did this in the second year, or maybe late in the first year of an undergraduate course. So, you know, the maths isn't actually that bad, but that's particle in a box. Now, the next thing I'd like to do is relate that to the hydrogen atom. If you thought that was bad, then the hydrogen atom, trying to do that for a hydrogen atom is horrendous, because instead of considering what's going on in just one direction, in one dimension, or particles trapped along a line, how simple is that? Well, we've just seen above that it's not like 2 + 2 = 4. exactly. With a hydrogen atom, you have to use, there are 3 dimensions, and you tend to use a coordinate system which is called spherical, if I could spell, is called spherical polar coordinates. So not Cartesian, spherical polars. And you know how Schrodinger's equation looks quite simple, relatively speaking, with just the x in it. When you translate into spherical polar coordinates, it changes to this, because you've got the radius, one angle in one direction, and then the other angle in the other direction. So when you start having to solve things in 3 dimensions, in spherical polar coordinates, the maths, it quickly becomes annoying. It's still just a matter of just grinding a handle and doing maths, but it's not something I could do. In fact, I'm not sure I could do this myself without like consulting a maths textbook, in all honesty. There is one bit that looks familiar though. Take note, second years. When, you know, this potential up here, Vx was 0 in our situation. When you've got a hydrogen atom, which is a positive charge in the middle, and an electron, the electron sort of sitting in the potential well of that positive charge, because this positive charge creates an electric field around itself, it's not that the electron is sitting in a potential well which is 0, it's sitting in a potential well which is given by this thing. So this is the Vx bit of the equation. That looks familiar, yes? Q squared over 4 pi epsilon naught r, electric potential. So what you do, the Vx that you put in, or in this case the Vr, is just the Coulomb potential, because a proton or a nucleus has an electric field around it. So at least that bit looks familiar to you. Now, I'm not going to solve that. You can go away and look it up if you really, really want a good evening. Needless to say, just as we get a range of wave functions here with different, specified by different, what are called quantum numbers, n, integers, which label the states, with a hydrogen atom, you get wave functions, which look more complicated. Indeed. So these are the radial components of the wave function. There's also another part of the wave function, which is to do with the direction in which you're pointing, right? Which has to do with the angles, but that, I've not actually included those. So these are the radial bits of the wave function. And do you notice something? You know how for the particle in a box, I just used n, didn't I? Whereas for these, there are 2 numbers, R10, R21. Because the hydrogen atom is more complicated and the electrons have orbital angular momentum, you have to label them with n, which is called a principal quantum number, and L, which is to do with the orbital angular momentum of the electron. So that's where you get, for those of you who do chemistry, 1, so n equals 1, L equals 0 is 1s. So that's n equals 1, L equals 0. N equals 2, L equals 0 is 2s. And you can guess perhaps what 2p then is. 2p is the 2p orbital is n equals 2, L equals 1. So the n and the L here give us our, 2s, 2p, 3s, 3p, 3d levels. Okay, so s is L equals 1, L equals 0, p is L equals 1, d is L equals 2, f is L equals 4. Right. this is just an example of, imagine you took the radial wave function and and in fact, before I do that, let me show you something. Let's see if this works. This is an applet, ignore the fact anyway, it doesn't matter. This is quite a nice, can I do this full screen? I'll just zoom in. The wave functions of hydrogen exist in more than one dimension, right? So instead of just waves that you could draw, they're like clouds they're a sort of three-dimensional wave function. So they're best sort of thought of as a kind of cloud, if you like. So 1s is very simple, right? It's just a sphere. If you've done chemistry, you'll remember that 2p is dumbbell shaped. So the wave function has quite a strong angular dependence. There's like lots at the poles and then not very much at the sides. As you get more complicated, so let's go to n equals 5 with f. So this is 5f. The wave functions really get quite complicated shapes. You can kind of see, if you look carefully at that, you can kind of see some waviness to it, in the sense that at some points it's like high intensity, some points it's low intensity. So you can almost see like a wave-like characteristic going on here in the sort of probability. And if you took a cross-section through that, so if I sliced through the wave function to sort of see what was happening radially, what's the best way of doing that? Let's go back to n equals 2. So if we took 2p and sliced through it, yeah, you can kind of see what's going on in one plane. And looking at these graphs, these plots here, show you what happens to the wave function here as we get further away from the nucleus. So it reaches a maximum and then gets smaller as you get further away from the nucleus. So you can think of this as the density of the probability cloud. And this peak, where this peak is approximately, would be considered the classical radius. This is just approximate, it's not as simple as this, but there'll be a sort of average radius which you could consider the classical Bohr radius of the atom. Okay. That is a lot to sort of take in. I said I'd do it, and I've done it. Now, I will, if anyone's got any questions, you can ask. So, if you think of any, just shout. So hopefully, particularly if you do chemistry, but also if you just do physics, I've shown you that you can, that basically the idea of a spectrum and only the electron only having certain energy levels possible arises naturally from the law we start with, or the model that we start with. That bears out in observation because you have all seen spectra, you know, colorful lines coming from elements. When you look at a spectrum, you're looking at, that's as close as you can get to seeing this idea that electrons can only have certain energy levels, because as you know, each spectral line corresponds to a transition between these different states, right? Excitation and de-excitation. So, you know, it's clear that there's something in this idea that electrons only exist in discrete energy levels. I will finish by showing you a short video, in fact. Some of you might have seen this morning if you were taught by Miss Burton, but I'm going to just show the rest of you anyway. Let me just forgive me for a minute. I'm just going to stop sharing my screen while I get this up. Here we go. So what I'm going to Okay, I've changed device. Hopefully you can still hear me. I'm going to play a YouTube video of me using a spectrometer, and towards the end there are some nice images of spectra. So I'll skip through it. So, I don't know if you can hear this. The spectra. Yeah. I'm going to first have a little tour of the equipment. So I'm going to come and grab the camera. And show you what we've got here. We've got I'll play the first bit. High voltage power supplies at the moment, they're not switched on. And here's the helium discharge tube. I've actually set the spectrometer up ready for the first measurement. And here's the oxygen discharge tube. That's the laptop. I'm going to be using the spectrograph, or it's actually called spectrograph software, to get the data from the spectrometer, which, by the way, is pretty much a box with a slit at one end, a diffraction grating inside it, and this camera sensor of a webcam inside it as well. So what I'm going to do first is turn the lights off, turn the helium spectral lamp on, and let's see if we can see anything on this. So there's the helium discharge tube, and look at what we can see here. I'm just going to set this down and turn the brightness back up, and to adjust the helium tube so that that's as clear as possible. You can see here that we've got a range of spectral lines in the visible part of the spectrum. Now what I'm going to do is place the images, or insert the images into the video with a suitable title. What I'm going to do first, while I'm still recording, is use the software. So we've got this spectrograph software. Now I think I'm connected to the spectrometer already. So if I click acquire, what I get is this. And you can see I've got a number of peaks here. Okay, so I'm not going to play the whole video, right? You can find it easily enough if you just type in Charterhouse Physics into YouTube. It's called Line Spectra, but at the end I put the spectra of about 6 different elements up. It's quite, quite pretty, if nothing else. If there are no questions, I think I'm going to call it a day there. I do